always like a little bit of yogic flying. Very nice. Well, this week I'm going to talk to you about index numbers. This is topic 3. It'll be a brief look at index numbers. I'll just tell you what you need to know. There's a lot of material about index numbers, and there are references if you want to follow it up. But in these series of short videos, I'll just be telling you really what you need to know in order to understand how inflation indexes are constructed and GDP and so on. Okay, well, enjoy, and I'll just go and settle into the transcendent again. So let's have a brief look at the theory of index numbers. So suppose you have information about prices and quantities. How do you combine these to give an overall index of prices? So what's the problem? What's the problem? Why should this be difficult? Well, the real problem lies in the fact that prices are in different units. So, for example, we might be wanting to look at the price of a main course meal, £5, let's say, or a litre of petrol, £1.30, or an hour's car parking, £2. Each of these things that are being consumed is measured in different units. A litre of petrol, an hour of car parking, a main course meal. Exactly the same issue arises when you're looking at real output. How do you combine different types of output into one big measure? You produce more cars, wheat, musicals, haircuts. How do you combine them? So if you were looking at something measured in the same units, there's absolutely no problem. For example, age, height, or weight. You could look at the British population and you say, well, take the average over a suitable sample of that population. So if you look at the average age of a British person now, it's going to be around about 40 years, the average age. In 1974, it would have been less. It would have been about 34 years. Because of life expectancy has been going up, the average age of a population has been rising along with it. Now, how do we solve this problem? Well, there's a simple method which is used, which lies at the heart of how price indices are done. And that is, you look at each item and you look at the growth in the price of that item, or more specifically, the price relative. What the price level is at time t relative to a base year, time 0. The point being that if that's a ratio of prices. It's a ratio of the price at time t relative to the same price at time 0. So it's a ratio, and when you take the ratio, the units drop out. So, for example, if the price of beer in July was £4 and in January it was £3, the relative price of beer in July to January is 4 over 3, 1.3. It doesn't have any units in terms of pounds or how much is in the pint of beer. It's simply an absolute number, 1.3, 1 1/3. So that when you look at price relatives, you get rid of all units of measurement, and then once you've done that, you get a raw number, and you can take some sort of average. And it's the same if you use a growth rate. If you think about a growth rate 5%, it doesn't tell you what's growing at 5%. Anything can grow at 5%. You don't have the units or what have you. So that's essentially the key insight which you should get from this slide. So let's first look at the problem. Let's assume that you know both prices and quantities. This has been an issue which has been looked at in some detail. Suppose you compare 2 periods, and in both periods you know the prices. There are n prices, PT1, PT2 up to PTM. P subscript T1 is the price at time t of good 1, PT2 is the price at time t of good 2, and so on. And t equals 0 is the base year, so P01 is the base year. price for good 1, and so on and so forth. So how do we do this? So L'Esper's, there's a first index, and essentially that uses the initial quantities to weight prices. So it weights each price by the quantity in its corresponding quantity in the base year. So it's like a price relative, the L'Esper's index. It's relative to the base year, and in the base year, of course, you've got the base year prices times the base year quantities. That's denominator. So that's a sum I equals 1 to n of pi0 times qi0, the price of good I in period 0, qi in period 0. So that's in the denominator. And in the numerator, we have the prices of goods in time t. So we have pit, but they're weighted by the quantities qi0, the quantity of good I in period 0. So if you like, the numerator, we're using the same quantity weights in the base year and in period t to give us our price index. So PL is the price index in period t expressed in terms of period 0. So that's it. This is actually named after Etienne L'Esper's, who was a German economist and a professor at Gießen in Hesse. You'll notice it's a French name. It's a French name because his ancestors were Protestant Huguenot refugees from France. Louis XIV kicked out the Huguenots in the early 18th century. So that's the L'Esper's index for you. The alternative to L'Esper's is what's called the Pasch index. And the difference is it uses the current period T quantities to weight prices PIT. So the Pasch index, in the denominator, it has the base prices PI0, each of them weighted by the QIT, the quantity at period T. And in the numerator, you have each price PIT is weighted by the quantity in period T. So that's the Pasch index. It's using what's often called the current period T quantities to weight prices, rather than the base period quantities to weight prices. It's named after Hermann Pascha, who was a German economist and a professor at Aachen. There's a photo of him. And in generally, there are a variety of different weights you can use, ways of doing it. You can use quantity weights from the past, before the initial period, and that's something named after Joseph Lowe, a British statistician in the early 19th century. And there are different ways of doing it. But the two main ones are L'Esper's and Pasch. So this brings us to the CPI, and it's a L'Esper's-like index, and I'm just going to show you why people say that and why it is, and also why it isn't. So the data for CPI is quite clear. You've got prices of different goods and services at different times. These are the PIT, P subscript IT, the prices of good I at time t, where I is a large number, many, many goods. So what you do is you transform the data into relative prices. That's the first step. So RI superscript 0t, RI is the price relative for good I, using the base year 0 at time t. That's defined as simply the ratio PIT divided by PI0. PIT is the price of good I at time t divided by PI0, the price of good I at time 0, the base price. So that's the price of good I at time 0 is really a reference point, base point. And we use this to express the price at time t in terms of its value relative to this reference point. And typically this reference point in CPI data is January of a particular year. So we have price relatives for each year, and they start off at 1 in January and then vary over the year, as you'll see in the data. The price relative is 1, unity, if the price is unchanged. It's less than 1 if the price falls, and greater than 1 if the price rises. R lies between 0 and infinity. Obviously, it's never going to be 0 or infinity, but it can lie somewhere in that range. So the inflation data we use is constructed by applying index number formulae to the price relatives as defined above, not the price levels themselves. This practice really dates back to Ronaldo Calvi, whose picture you can see on the first slide, the opening slide. So this is it. Inflation uses indexes, and the indexes are based on price relatives. Now, here we come to one of the most important equations in this video. It's an equation which shows how you move from price levels to price relatives and using expenditure shares. So let's start from our Laspers index. It uses initial quantities QI0 to weight prices PIT. So we start off the first line of the equation. We've simply got our Laspers index PL at 0t is equal to the sum of I equals 1 to n PIT times QI0 on the numerator. So the PIT, the prices at time t, are weighted by quantities QI0, the base period quantities, divided by the sum of PI0, QI0, the base prices PI0 times the base quantities QI0. So the sum of PI0 times QI0 is simply total expenditure in the base period 0, price times quantity for each of the I goods in the base period. The numerator is a hypothetical revenue where the prices in time t are multiplied by the quantities in time 0. So it's, if you like, the revenue that would have been how much the initial quantities QI0 it would have cost to buy them with period I prices. That's essentially what the Laspers index is. So now we move along at the top line, equals, and now we do a little trick. So the denominator remains exactly the same. It's the total expenditure in period 0, the prices times the quantities in the base period. But the stuff happens in the numerator. So what we do in the numerator, we take our each term PIT QI0 and we multiply and divide it by PI0. So it's a free country. If you multiply and divide something by a positive constant, it leaves it unchanged. So what you get then is you get the summation now of two things. So there's the first bracket, PIT divided by PI0. That's the price relative. It's the price of good I in times t relative to the price in time 0, price good in time 0. Then we have the second bracket, which is PI0 times QI0. Well, that's the price of good I in time 0 times the quantity in good I in 0. That's the expenditure on good I in period 0. And the numerator, we sum this up over all of the I products. So we can write this because the denominator is the total expenditure on goods in the base year, and each element in the numerator, we've got the expenditure for each good I. So what we can do is we can rewrite that in the thing that's at the end of the top line, which is the sum I equals 1 to n of the price relative for good I, that is in the bracket PIT divided by PI0, that's the price relative for good I in type t. And we multiply each one of these price relatives by SI0, where SI0 is the expenditure share of good I at time 0. So SI0, that's in the second line, is simply defined as the PI0 times QI0, that's the expenditure on good I at time 0, divided by the sum of that, the sum of all of the PI0s, QI0s, all n of them. So that's total expenditure. So it's a sum, it's what's spent on good I in period 0 divided by total expenditure in time 0. It's the expenditure share at time 0. So we can write it more succinctly still as simply saying the Laspers index is simply equal to the average of the price relatives, RI, where it's a weighted average where they're weighted, each price relative is weighted by this SI0 expenditure shares at time 0. So what we've done is we've taken the standard Laspers index, which is expressed in terms of prices and quantities, and we've re-expressed it exactly the same value in terms of price relatives and expenditure shares. So it was actually Irving Fisher that realized you could do this, that you could rewrite the Laspers index in terms of expenditure weights. Laspers himself always thought you needed to have quantities. Now, if we turn now to the PASH index, you can use exactly the same procedure. And that's it. So we start off, PASH uses the current quantities to weight prices. So that's the ratio of sigma PIT QIT in the numerator divided by sigma PI0 QIT in the denominator. So we can proceed with the same method, but this time we do it in the denominator, not the numerator. So we take the numerator, and each term in the numerator, in the denominator, sorry, we multiply them by PIT and divide by PIT. So sigma PI0 QIT becomes sigma PI0 divided by PIT times PIT times QIT. And so if you rearrange that, it becomes something that's a little bit like what you've got in the square bracket, which is it's a weighted average of 1 over the price relatives. That's actually what's called a weighted harmonic mean of price relatives, where the weights are given by the expenditure shares at time t. Sorry, in the figure that it's a capital T, it should be a little t, but it doesn't really matter. So the weights here are expenditure shares. L'Esper's uses the initial period, Pash uses period. In the previous slides, we've looked at how we can rewrite L'Esper's and Pash in terms of price relatives and expenditure shares. I'll just make a couple of comments here. As a quick note, there's something called the index number problem. And this asks the following question, if you like. Can we combine both the price and quantity data over time to obtain a measure of both the relative changes in general price level and the general level of output? That is, can we consistently combine data to get a price index and a quantity index that are consistent? Now, for CPI, we don't really need to worry about this index number problem as such. It's not really an issue because we're only looking at prices. We're not bothered about quantities here, so how you do real output. We'll look at that in the next semester when we look at GDP. Certainly, in practice, CPI is L'Esper's-like. The reason is because the information on weights is old. So it's not actually L'Esper's because the price relatives are with respect to January, but typically the weights we're using the weights from the previous year's expenditure shares, which are typically gleaned from the Living Costs and Food Survey and the National Income Accounts, the data on household final consumption. So typically then the CPI index uses weights which date from the past, the previous year. And in fact, in early years, it could even be much earlier. So for example, when RPI was first constructed in 1947, they were using expenditure share data that was collected before the Second World War in the late 1930s. So we call it L'Esper's-like. It's not it's a bit like a L'Esper's, but the weights are old. So technically, it's a low index, really. Within the year, of course, the price relatives are made with respect to January as the base price. So that's the case. So the price relatives are within the year to January, but the expenditure shares are a little bit later. Look what happens if you know the quantity, prices and quantities. You can use L'Esper's or Pash indices. If you don't know quantities, but you know expenditures, then you can express L'Esper's and Pash in terms of price relatives and expenditures. But what happens if you don't know anything about expenditures? So when we don't know anything about expenditures, typically we take the price relatives and we simply take a mean. So the mean is usually either arithmetic, in which case it's called Carli, or geometric, in which case it's called Jevons. So obviously, Carli is a gentleman we saw earlier, the Italian from the 18th century. He obviously, the arithmetic mean wasn't invented by him, but applying it to price relatives in this context of doing a price index, that is what it's called, a Carli index. And also Jevons didn't invent the geometric mean, but in applying it to price relatives in this context, he was the first person to do that. So suppose we don't have expenditure weights, we use these simple averages. So we've got Carli there, it's simply the arithmetic mean. So in the case of two goods, it's R1 plus R2 divided by 2. Jevons, it's a geometric mean, which in the case of two goods is square root of R1 times R2. So Stanley Jevons was a British economist based at Manchester mainly, and his son Herbert, or also known as Harry, was a professor at Cardiff here in 1906 to 1910. The economics department in Cardiff is very old, and certainly much older than the business school, The business school was built up in the late 1980s. Anyway, let's move on. Let's take a simple example. So if R1 is 1 and R2 is 1.5, this gives us Carley arithmetic average of 1.25 and a Jevons of the square root of 1.5, which is 1.22. Now, you'll notice there Jevons is less than Carley. Well, that's because a geometric average is less than an arithmetic average, except when all elements are equal. So the Jevons and Carley index are equal if and only if all price relatives are equal. Otherwise, Jevons is always lower than Carley. So let's just look in a little bit more detail here. So here we have a diagram. So on the x-axis, you've got R1, price relative for good 1, and on the y-axis, you've got R2, the price relative for good 2. The dotted 45-degree line is where R1 is equal to R2. And if we look at the level of Carley, which gives you a particular value of the Carley index, that is R1 plus R2 equal a constant, or the average equals a constant, that's simply a straight line like the one you have there. That's the negatively sloped 45-degree line. Obviously, as that shifts out further and further out, you've got a higher Carley average. But along that line, the average is exactly the same. That's why it's called iso-Carley, the same value for the Carley index. The Jevons, iso-Jevons curves, those are a rectangular hyperbole, technically speaking. So it's the values of R1 times R2 which give you a particular value. So these look a bit like Cobb-Douglas indifference curves. That's because basically it's the same formula. And of course, as you move out, further out, it's becoming higher. So we've got J2 intersects the R1 equals R2 line, the 45-degree line, where at the same point as it intersects a negatively sloped iso-Carley line. So at that point, R1 is equal to R2, so the Carley is equal to the Jevons, and the Jevons is J2. As we move along the iso-Carley line, we're keeping the Carley index, the arithmetic average, the same, but the Jevons index will be falling, as we can see. So that, for example, if you take a point J1, for example, that there are 2 points where J1 intersects the original iso-Carley, they're relatively unequal, and at those points, J1 is less than J2. And any point along the iso-Carley line, which is away from the R1 equals R2, will give you a lower value, will be on a lower iso-Jevons level, a lower level for the Jevons index. So that's basically how it is. So you should know this, that a geometric average is less than a arithmetic average. So let's have a look at a couple of examples. So for the second example, we'll have the same Carley but a lower Jevons. So we've got R1 equals 0.5 and R2 equals 2. In this case, the Carley is exactly the same, 1.25, but the Jevons is now lower at 1 because the geometric mean of 0.5 and 2 is 1. So that's a bit like the point where J1 intersects the iso-Carley line there. A third example is where R1 equals 0 and R2 equals 2.5. Again, the Carley is unchanged. It's equal to the average of 0 and 0.25 is 1.25, but the Jevons is 0. And of course, when you have a 0, any geometric mean will be 0 if any one of the values is 0. So that's an example there. That's an extreme example. When there's a lot of price dispersion, you tend to get a lower Jevons than you do a lower Carley. Than you do Carley. Oh, this video has gone through a little bit of the maths underlying various indices. And essentially, an index number is something that enables you to combine objects measured in different units. And the way it does this, for inflation at least, is to use growth rates or price relatives so that these don't depend on the units of measurement. And it combines these price relatives in a way, give you your price index. So if we go back in history, this index number problems was looked at in the 19th century. And we've got the classic measures which you come across in the textbooks are Laspairs and Pasch indices. But for these, you both need both price and quantity information. But you can actually use expenditure shares. Having expenditure shares is as good as having quantities. And it's observable. Expenditure is a common measure for all types of goods and services. And of course, expenditure is measured in pounds or dollars or whatever. And so it's not, it doesn't suffer from the problem of being measured in different units, which you had with quantity. So you can weight price relatives by expenditure or expenditure shares. So the Laspairs index can then be expressed as an expenditure weighted mean of price relatives, the Pasch index as a weighted harmonic mean of price relatives. Now, if you don't have expenditure data, then what you can do is you can use unweighted means, and the two that are used by the ONS and statistical offices in general are the Cayley, or the arithmetic one, and Jevons, which is a geometric average of these price relatives. So these two measures of methods are equal if all price relatives are the same, but in general, the arithmetic exceeds the geometric when price relatives differ. And that's really the basis of what's called the formula effect. Okay, well, thanks for that. That's the general summary. So that's the end of video 1. In the next video, I'll be looking at what happens, the economics, if you like, of price indices. What are the theoretical ways of evaluating whether an index like the Cayley or Jevons is good or bad? So we'll talk about that in the next video. Okay, well, thanks for listening, and see you in the next video.